Topic 7.1 Magnetic Force. Current carrying conductor in a magnetic field. If the conductor is perpendicular to the field, it can be noticed that the force F on the conductor is proportional to the current I, and also the force F is proportional to the length of the conductor L. Combining these two equations and introducing a proportionality constant B, we can write this relationship as follows. F equals BIL, where B is called the magnetic flux density. Since B equals F over IL, magnetic flux density B can be defined as the force per unit length of a conductor carrying a unit current. SI units of magnetic flux density is newtons per meter per ampere, which in turn equal to kilograms per second squared per ampere, which is the derived unit named Tesla. Dimensions of magnetic flux density is mt squared. If the conductor is inclined to the field with an angle theta, magnetic force on the conductor F equals BIL sine theta. This is the general equation for magnetic force on a current carrying conductor. If the conductor is parallel to the field, theta equals 0, and therefore F equals 0. Fleming's left hand rule. If the thumb, index finger, and middle finger of the left hand are stretched to be perpendicular to each other, and if the index finger represent the direction of magnetic field, the middle finger represent the direction of current, then the thumb represent the direction of force. Charge moving in a magnetic field. If the velocity v of the charge is perpendicular to the field, F equals BQV. Direction of force is given by Fleming's left hand rule. If the velocity v makes an angle theta with the direction of the field, F equals BQV sine theta. This is the general equation. If the velocity v is parallel to the field, theta equals 0, and therefore F equals 0. Hall effect. Hall effect is the production of a voltage difference, which is called the Hall voltage, across an electrical conductor transfers to an electric current in the conductor and to an applied magnetic field perpendicular to the current. This effect was discovered by Edwin Hall in 1879. Derivation of an expression for Hall voltage. The figure shows a rectangular cross-sectional current-carrying conductor whose sides of the cross-section are A and T. respectively. If we maintain a magnetic flux through the conductor perpendicular to the conductor, the drifting electrons will be shifted upwards due to magnetic force. Therefore, an electric field is created directed upwards. Voltage difference also created as shown in the figure. Once the steady state has been achieved, the magnetic force on the electron will be equal to electrostatic force on the same electron. Once the steady state has been achieved, the upward magnetic force on an electron will be equal to the downward electrostatic force on the same electron. Since electrostatic force is given by F equals EQ, Fe is the electrostatic force, E is the electric field strength, and simple E is the electronic charge. Say equation 1. Since a magnetic force on a moving charge is given by F equals BQV, magnetic force on an electron can be written as follows, where Fm is the magnetic force, B is the magnetic flux density, simple E is the electronic charge, Vd is the drifting velocity of electrons. Say equation 2. At a steady state, Fm equals Fe. Therefore, we can write as follows. Since electric field intensity is equal to the potential gradient, we can write as follows, where E is the electric field intensity, Vh is the voltage difference, which is called the Hall voltage, A is the height of the conductor. Say equation 4. Furthermore, we can write the current in terms of drifting velocity of electrons as follows. Say equation 5. Combining the equations 3, 4, and 5, we can write as follows. Since T is a constant for a given setup and can be measured, N is a constant for a given material and can be found out as a data, is a non-constant, and VH is a measurable quantity. This relationship is the principle behind the sensors used to measure magnetic flux density.